We are starting now Unit 5. Unit 5 is part of these compound events. In other words, two or more things happening at the same time. And all of Unit 5 can be summed up with multiplication rules. Now, there are two special events that happen with these compound events. So compound events, once again, two or more things happening. And these events could either be independent from each other or they could be dependent from each other. Independent means one event happening or not happening does not change the probability of the second event. For example, if I roll 2 dice, the first die does not affect the outcome of the second die. If I flip a coin, the first flip does not affect the second flip. If I pull a card from a deck of cards, that one can be a little bit tricky. If I pull a card and I put the card back to pull a second card, it doesn't affect the probability. Because the first one we started with 52 cards, pulled the card, put the card back, we still have 52 cards. However, it could also be dependent. In other words, one event happening or not happening changes the probability of the second event. So going back to the pulling a card, if I pull a card, I had 52 cards in the deck. But if I set that card down and not put it back, I now only have 51 cards. So that does change our probability. If I'm pulling marbles from a bag and I don't put the first marble back, that changes the second probability. It changes our total. In general, we have 3 formula to use. The one that we're going to use the most is the multiplication rule for independent events. I do want everyone to make a note. I call these our AND probabilities. So if you see a probability of rolling a 2 and an odd number, that would be a multiplication rule. Once again, because we said and. And all that this means then is the probability of event A and B is the probability of event A times the probability of event B. I am going to look down at the conditional probability. What a conditional probability is, and it's read as the probability of A, and that vertical line means given B. And what that basically is saying, for example, the probability of a junior given they're a male. So we have a condition attached to it. The condition is that they're male. So we don't care about all the females. So we're only looking at the males in that case. We will talk about the conditional probability later, actually more in the second half of this unit. But do make note for the multiplication rules for conditional events. We have 2 options. Probability of A times the probability of B given A. Or the probability of B times the probability of A given B. And once again, I will talk about those 2 later. We're mainly only going to be focusing on the multiplication rules for independent events. I'll also show you guys an example of dependent events. So example 1. Suppose you're going to throw 2 fair dice. First, before we even start, is this event independent or dependent? Well, ask yourself, does the first die affect the second die? It doesn't, so this would be independent. So the first question says, what is the probability of getting a 5 on each die? So our first die, we want a 5. So the probability of getting a 5, well, there's 1 5 out of 6 sides. That's for your first die. For the second die, once again, there's still 1 out of 6. Now, quick recap of how we multiply fractions. Well, we multiply across. So 1 times 1 gets us 1. 6 times 6 gets us 36. Second part, what's the probability of getting an even number and a 7? Well, even number, there are, well, on a die, 2, 4, and 6. So 3 of them out of 6 are even. And, so times. Are there any 7s on a die? No. So there are 0 7s out of 6. Multiply across, we get 0 out of 36. Or if you just want to write it as 0, you can. I'll accept either. Go ahead and try the third one yourself. It says, what is the probability of getting a multiple of 2 and a multiple of 3? Once again, and means to multiply. So multiple of 2, so 2, 4, 6. So there are 3 options out of 6. And means to multiply. Multiple of 3, 3 and 6. So 2 out of 6. We're going to multiply across. So 3 times 2 gets us 6. 6 times 6 gets us 36. Example 2. Example 2 says your vehicle has a 75% chance to start when it is cold out. If it does not start the first time, you try again, which is successful 85% of the time. What is the probability that your first time is unsuccessful and the second time is successful? So the and, once again, tells me we are going to multiply. It'll be something times something. So the first part, we want it to be unsuccessful. But we know it's successful 75% of the time. So it's unsuccessful. The converse, or the complement of it, is 25%. Now, it's weird trying to multiply percents, so I am going to put it as a decimal. So 25% as a decimal is just 0.25. But we want the second attempt to be successful, which is successful 85% of the time, or 0.85. Multiplying those two numbers, once again, it was an and. We end up getting 0.2125, which is the same thing as if we move the decimal right 2 spots, 21.25%. Now, the question is, how do we determine if an event truly is independent? Especially from our relative frequency problems. Well, in order to prove two events are independent, the probability of event A has to be the same thing as the probability of event A given B. And we're going to look at that in this example 3. According to example 3, students are sorted. Mr. Johnson needs to fix that typo. Are sorted randomly into 4 houses at a certain school seen below. So there are A, B, C, D, and we have total, boys, girls, total. This is called our contingency table. We're actually be making these in the second half. So real quick looking at it, I can see 75 boys are in group A. I can see 6 girls are in group B. I can see I talked to or sorted 350 total people. So for A, it wants to know the probability of A, so probability of house A. So the total number of people in house A is 124. Out of, because we're doing a probability, 124 out of 350. B, this is our first conditional probability. And conditional probabilities truly are not that bad. It says the probability of A given they're a boy. Once again, that vertical line means given. So because we know it's given boy, I'm only looking at the boy row. So how many boys are in A? So 75 out of 162. And then C, determine if the class you get sorted into is dependent of gender. Once again, it gets up with this. Those two probabilities have to be the same. Now, it's real hard to compare fractions with different denominators with different bottom numbers. So I am going to convert them into a decimal or approximate them. So if I type that in the calculator, we get roughly 0.35. Meaning there's roughly a 35% chance that you'd be sorted into house A. And if I do the same thing for the second one, get roughly 0.6. Meaning there's about a 60% chance that you get sorted into house A given you're a boy. Now, to answer this last bit, once again, this probability has to be the same as this probability for them to be independent. So to determine if they are dependent, those decimals or those fractions are not the same, so they are dependent. Once again, because 0.35 does not equal 0.6.